Hello, good afternoon, everyone. I'm Deepak, and I work for Adobe Systems. I also have my colleague Vijay Srivastava. First of all, thank you for attending our talk. Hopefully, you will find it interesting enough, and I will not make you fall asleep during this post-lunch session. Before we start, let's do a quick show of hands to see how many of you are data scientists or machine learning scientists. OK, almost everyone. Data or machine learning engineers. OK, and managers. OK, thank you. So I manage a team of data scientists and data engineers at Adobe. And Vijay is one of our lead developers. So if things go right, you know who to give credit to. And when things go wrong, you know who to blame. So now that you have told me a little bit about yourself, let me give you a brief idea of what our team does. Our team is responsible for building ML core services, which are core machine learning and AI services that are targeted to Adobe Sensei applications. So Sensei is a brand name, which is or a branding that is used at Adobe for all the AI and machine learning algorithms across all Adobe products. So there are a couple of examples of services that we build. For example, we have a service targeted towards data quality, summarization, and visualization. As you heard today morning in the keynote, 80% of time data scientists spend in cleansing their data and dealing with data quality issues. And the 20% of the time they spend complaining about it to us, we try to build solutions that help them be 100% productive. Continuous model evaluation is another service which helps with monitoring models that are in production deployed and generating alerts when things go wrong. And we have a talk about it tomorrow at 11 a.m. Please attend. Vijay will be presenting about the details of model evaluation. Causal inference is another service where we are actively looking to look at causal relationships between dependent and independent variables rather than plain correlation that is used for most parts. And finally, model interpretation, which is the talk today. Talk deals about how to interpret models, which is how to understand why models are behaving in a certain way, why they're classifying certain things as cats and certain other things as dogs, and so on. So let's get into the details of this talk. In this talk, we'll understand what we mean by model interpretation, why is it needed, how people do it today, and what changes we did, and how we optimized to solve various problems that we had. Part of this talk is research-oriented and partly engineering. Hopefully, it will be interesting to all of you. To start with, first understand what is model interpretation and what exactly we mean by it. Interpretation is the ability to understand why a model is behaving in a certain way. Why is it classifying or doing regression and coming up with predictions in a certain way, right? Which features of the models are making it take certain decisions in terms of classification or regression? Which features is it treating more important than others? Some of the models are inherently interpretable. For example, linear regression. So one can look at the coefficients of the regression model that we build, and interpret it directly. So that is an example of a global interpretation. Another example where a model is naturally interpretable is a decision tree, right? So we can look at the tree and read the rules as we can read the tree as a bunch of rules, and that is inherently interpretable. Although it is arguable to a certain extent that if you have too many rules and the rules have too many predicates, then it becomes harder to interpret, to look at it as a bunch of if-else statements. Certain other models, such as deep neural networks that are very popular now, although extremely accurate, they are not well interpretable, and they work more as black box models. And we do understand, again, from, for example, today morning's keynote, we see that certain models try to learn certain behavior, and they are not always ideal. For example, the StarCraft that the keynote speaker today morning was trying to learn, the model learned a particular gameplay that he was not very happy with, and they improvised the model in various other ways. So coming back to model interpretation, there are two ways of looking at the interpretation. One is global, and the second one is local interpretation. So to give you an intuitive sense, global interpretation means at a high level or a summary level, what is the model telling us? For example, coefficients of a linear regression. At a global level, feature 1 is more important over feature 2 and feature 3 and so on. And feature 5 might not be relevant at all for the model's decisioning. Local interpretation, alternatively, looks at a single data point and tells which features are more important in the classification that the model did for that particular data point. For example, let's say we have a credit monitoring, credit scoring application, right? And typically, the global interpretation might be that your credit score is the most important factor for deciding whether you get a loan or not. And a local interpretation, which not always agrees with the global interpretation, might be you have a great credit score, but then we are declining you a loan because maybe your age is too high or something like that. And this area, of course, has been an area of active ongoing research. So now let's see what are some of the top reasons why we need model interpretation. The first one is there is a general scare of moving towards a black box society, in which increasingly more and more decisions are being made or algorithmically by these models that people don't understand. Secondly, as part of GDPR, there is a right of explanation. So whenever there are models that are taking decisions involving a certain person, then the person has the right of explanation. So if I'm denied a loan application, then I have the right to ask why. Third, we don't want the models to discriminate based on ethnicity, race, and gender. Moreover, data scientists also would like to understand why the models they have built are working in certain ways. And not only to do sanity tests to make sure that they are going along the right direction, but also to convince the business owners. Right? And business owners, for example, are primarily interested in the model understanding because they want to make sure that it aligns the decisioning process that the model is taking, aligns with the domain knowledge that they have. Let's look at some of the state-of-the-art work that exists in this field. The first one is LIME, which stands for Local Interpretable Model Agnostic Explanations. The second one, SHAP, which is short form of Shapley Additive Explanations, and that comes from the domain of game theory. So let's go into the details of each of these and see what they do. So coming to LIME, so here in the diagram, what you see is a decision surface from a model, particular model. So red and blue are two classes, and you see that the model decision boundary is a highly complex, nonlinear, non-convex surface. So what you see here with this plus in bold is the data point that we are trying to explain. Right? So we are trying to come up with a local explanation for this plus in bold red. The way LIME does is, it samples a bunch of nearby points, and it assumes that it has access to the model's scoring function. So it takes each of these points that it has sampled. So you see a bunch of points here in circles and pluses. LIME uses these points and runs it through the model that it's trying to explain. So the model returns a bunch of scores and labels for each of these points. Right? So some of these points you see here in blue are labeled as blue circles, and the others are labeled as red plus marks. Also, what LIME does is it weights the points based on their nearness to the point of interest. Right? Point of interest being the item in bold. So you see here again the points which are very close to the point of interest are shown in higher, or they are shown as bigger circles or bigger plus marks, which are over here. as compared to some of these which are shown smaller because they have lower weights. So based on this weighted approximation, it comes up with a linear boundary, right? So it builds a linear classifier, and that is the black line that you see here. So the linear boundary forms as a local explanation based on line. The coefficients of this line are useful for, so here, for example, it's a two-dimensional feature space, and the coefficients are used to determine which features are considered more relevant by the model as compared to others. So that is about the local explanation. What Lime does to come up with global explanation is to aggregate these local explanations over a variety of points and then aggregate them in some form to come up with global explanation. So in the interest of time, I will not go into the details of the global explanation. You can find more details on the paper that I have referenced here. So what's the problem with this approach? The problem is every time you are trying to explain a data point, every time you are trying to come up with a local explanation, you need to sample points and you need to build a linear model, and that is compute expensive. Also, the sampling method is not always, using a uniform sampling is not always optimal, and your sampling needs to be dependent on the data distribution and so on. And that is not always straightforward. Let's look at what Shapley value does. As I mentioned, it comes from the context of game theory, wherein the setting is this. We have a group of people, and each person or a team has a certain inherent value that they contribute towards a certain task. For example, people work individually or in teams, and the task it's any general task where you have to achieve a certain objective, and you get a reward or a profit for achieving that objective. So Shapley, the idea of Shapley value is to come up with a distribution of the rewards towards each individual based on what they contribute towards the task, right? And in a team setting, it is not always trivial because you can't distribute the rewards uniformly over the team members. So let's see how Shapley tries to do it. So let's say we have n people, and the number of, so you essentially come up with a power set of all these n people, right? So power set is the set of all sets. So we have a set with one person, we have a set with two people, three people, and so on. And if you consider a set of two people, you have n choose two ways of building that set, right? So you come up with power sets, and let's see what you do with each of these sets. So let's say you have a set of 4 people, right? And now you are trying to see, you have a set of 3, and now you want to add the 4th person to the team. Now, what is the value that the 4th person contributes to this team is you have a value function that gives you the value or the profit per in the team setting, right? So you compute the value without this person, value of the team without this person, and you compute the value of the team with this person. And the difference is the value that is contributed to by the 4th person. Given that we have multiple such enumerations or sets, you do this over all possible enumerations where the 4th person is involved and average it, and then that gives the contribution or the reward that this 4th person is entitled towards. Okay, so let's see how that idea is used in the context of getting feature importances. So in the example that I described, replace each individual with the features that are used in the model, right? So you try to look at, if there are 10 features in a model, you try to look at 1 feature, 2 feature, 3 features together, and then look at some, you have to come up with some value function, which could be, say, for example, an accuracy that the model has using only 3 features, only 4 features, and so on. And then in a similar setting, you can compute the value that each individual feature adds to the model. Nice, looks fair, right? So what is the problem or the catch here? The problem is it gets computationally intensive to compute this over all possible enumerations of the number of features that you have, and you need to do it for each of the data points. So your compute grows exponentially with the number of features as well as the data points. So now that we have looked at two of the prominent methods that are in academia and industry, let's see how we solved it. So this is a general outline of our approach. We first build prototypes, which are representative examples of the data. Then we come up with something called as ally and adversary. I'll go into the details of what they mean. The Voronoi regions that are formed by the prototypes define our global interpretation, and then we use univariate distances based on ally and adversary to come up with local explanation. So I'm sure this slide is probably confusing to most of you, so let me go into the details. What are prototypes? As I mentioned, prototypes are representative samples from the data with certain desirable properties. Right. So the prototypes help us significantly compress the data and reduce the compute without compromising the interpretability. There are in literature there are multiple ways of generating prototypes, and we assume that you use one of the methods that is best suited to come up with the prototypes. We in particular use the one proposed by Bean and Tipshirani. So let's see how that looks. This is a toy example which has 2 dimensions or 2 features. So the data is standardized, which means to say that it's centered at 0 mean and 1 standard deviation. So you see most of the data spread between -2 and +2. The small dots that you see are the individual data points, and the larger circles that you see are the prototypes. So here you see that there are, say for example, 3 classes, ones indicated by red, green, and blue. Also, you see that there are, say, hundreds of data points, which are now compressed to about 30 prototypes. And the prototypes are well spread so that they capture most of the variability that lies in the data. Now that we have generated the prototypes, let's see how we use them to come up with local explanations. So say the black circle that you see here is the point of interest that we are trying to explain, right here. What we do is, among the prototypes that we have, we try to identify an ally and an adversary. So what's an ally? Based on the model, the point of interest was classified as belonging to the red class. So we find a prototype, a nearest prototype to the black circle, which is the point of interest, which happens to be this ally, right? So we are calling the nearest red prototype as the ally, and the nearest prototype, which does not belong to the red class, as the adversary. And this happens to be the one here, which is blue in this case. Based on ally and adversary, we find a perpendicular bisector to the line that connects the ally and the adversary, right? That line happens to be this black line that you see here. And this is, in some sense, is an approximation of what LIME does in trying to find the model separating hyperplane or the separating boundary. As you would see here, this approach is much simpler in as compared to LIME, and we are able to achieve a similar outcome, that is to find the separating hyperplane. Now that we have a separating boundary, let's see how we come up with explanations. So this is the same setting again, minus all the other data points that are not relevant to us. So once we have the point of interest, ally, adversary, and the boundary, we look at signed distances from the boundary to the point of interest. Sorry. And we weight them. So we come up with weighted signed distances, and that forms our local explanation. So I'll go to an example. So here we are looking at a popular data set that is used in academia, which happens to be the iris flower data set. So it has 4 features, which are petal width and length, sepal width and length, and it has 3 classes, which are versicolor, sentosa, and virginica. So on the bottom left, you see one plot, which is a local explanation for a point that was labeled as versicolor. So what our local explanation, our model is saying is, so the blue that you see here is the value, feature value of the point of interest. The green is the value of the ally. the feature value for the ally, and red being for the adversary. So on the left bottom plot, what you see here is the model stating that petal width, length, and sepal length happen to be the dominant factors that resulted in this data point being labeled as versicolor. And sepal width had no impact in this classification. Similarly, you see other examples for data points which were labeled either Sentosa or Virginica. Cool. Now let's go to global explanation. So I described a method for coming up with local explanation. We apply the same method for each of the prototypes of each class of labels that we have. And we then aggregate them to come up with global explanation. So in the previous example, you saw that we had petal width, petal length, and sepal length as the features. So we do have feature weights that we apply in order to come up with local explanations, and they are aggregated to form the global explanations. So let's look at an example of how the global explanation for this looks like. So we have on top left, for example, global insights for the class of Sentosa. So what we say, what the model states here is sepal width happens to be the most dominant factor in labeling, in data points being labeled as Sentosa, and sepal length happens to be the least dominant factor. So far, so good. Neither did we have to build a linear boundary for every data point that we had to come up with explanation for, nor does our method grow exponentially in compute over data points and feature space. But what's the catch here? So the catch is in the complexity involved in computing the prototypes, which based on the method that we used required us to look at pairwise distances between each pair of points, which happens to be n square. Right? So if you have millions, if not billions of data points, then the compute in terms of looking at these pairwise similarities grows prohibitively. So how did we solve this problem? We use something called as locality sensitive hashing, in short for LSH. So here in this picture, you see two features. There are a bunch of points, but assume there were millions of points. And you are trying to solve the problem of trying to do a pairwise distance between each of these points. How do we do this? The idea is simple. So what you do is you draw a bunch of random lines. Right? For simplicity, the lines are passing through origin, but without loss of continuity, we can assume there are any random lines. So these lines, along with the two axes, x and y axis, split the number of data points that we have into multiple bins or buckets. And the idea is that you have to look at only the points that lie within the same bucket and compute the pairwise distances between them, rather than looking at all possible pairwise distances. Let's see why this works. Let's say these are the 2 points that we are trying to compute the distance for. And theta, which is a cosine distance, is the angle between the 2 points. So the idea is, if the points are very close by, the closer they are, the smaller is the value of theta, right? And the smaller is the value of theta, the probability that at any random line that you draw splits these 2 points into different buckets becomes smaller and smaller. And to be precise, the probability is theta over pi, pi being 180 degrees. Right? Hope that is clear, because that's the key idea here. As the points are closer together, the angle between them is smaller, and the probability that any random line splits the points into different buckets becomes lower. Even with this, there is a non-zero probability that 2 nearby points fall into different buckets, and you would miss out on computing the pairwise distances between them. So how do we solve the problem? One way of solving the problem is by looking at points which are in adjacent bins. So instead of looking at points which are in the same bin, you also look at points which are in immediate adjacent bins. The second way of solving this problem is by building multiple hash tables. So what we simplistically described as drawing random lines is actually in practice implemented by using hash tables. So you come up with a good hash function that can partition your data into multiple buckets, and you look at data points which are within the same bucket. Right? So here in this first case, on the plot on left, you have a hash function that is splitting your data into 7 buckets. The second idea for improving the accuracy of this method was to have 2 functions rather than 1. And you look at data points which fall in the same bucket, not just based on the first hash function, but also based on the second hash function. Right? And without going into the details of the math, we can state that using more and more hash function reduces the probability that the data points that are close by fall into different bins, lower and lower. So now that we know how LSH works, let's see how it is implemented in Spark. So we use this, so this is a code snippet from a Spark documentation page. We use this function called bucketed random projection LSH. You need to provide a bunch of parameters to it, which is the number of bucket length, which is the number of bins in which you want your data to be hashed, the number of hash tables to use, the input columns, that is which columns do you want to consider to come up with the distance, and the output column, which is the column where the hash, the data points, when they are hashed into a particular column, you have the labels of which bucket they belong to. So when that is done, we call the fit method, which builds out these hash tables, and then we call the transform, which assigns the data points to one of these hash buckets. So once you do all that, you can call the approximate similarity join function that with certain threshold that will give you all the points that lie within the given threshold. And using that, we can the complexity of having to compute the prototypes becomes much easier for us. To do a quick recap of the approach, we first come up with prototypes. We use the ally and adversary model to come up with local explanation as well as global explanation based on the prototypes. And finally, we use locality sensitive hashing to reduce our compute complexity and avoiding to compute pairwise distances. And that brings us to the end of the talk, which is incomplete without thanking these folks, Joshua, Debraj, and Vijay, who contributed in this project. And with that, I can take some questions.
Thank you for the talk. I'm wondering, how do you assess the quality of the explanations of the last model?
Thanks. So the question was, how do you assess the quality of the explanations? So that is a subjective point, because even in the literature, in academic literature, if you look at it, the quality of the explanations has mostly been evaluated based on primarily 2 criteria. One is the fidelity of the explanation as compared to the model that you are trying to explain, right? So if you use if you consider 2 models, one which is computing these classification labels or regression values, and the second your model which is trying to explain this. And if you look at the accuracy of your model with using the original model's output as the ground truth, then how accurate is your model? If your model is stating contrary to what the original model is saying, then it is not accurate, and hence it's not a good explanation. If your model is 100% or close to 99% to the ground or to the original model, then it's better. So that is one way. The second way is by doing user studies. So the local and global explanations that you come up with, you give it to a bunch of users and say they might be domain experts, and you ask them, does it make sense? And you can do a user survey to see if what they say, and based on that you could judge. Second way of doing the same thing is doing user study is to ask the users if it helps them to maybe action on the data or take some decisions based on the explanations that you give them, right? For example, let's say if it was a credit scoring application and the model gives out a prediction. And just based on the prediction, if a banker had to decide on your loan application, can he do it well enough? Or if you supplement the model's outcome with the explanations to say that the loan has been declined because the income is too low or the credit score is bad, will that help the user do better judgment? So these are some of the ways that you evaluate them.
Okay, do we have any other questions in the audience? Here we go.
Thanks for your presentation. I think it was really insightful. I have a question about the prototypes, because you mentioned that you try to look for a close prototype. And you mentioned something, I think, that the prototypes have some desirable properties.
Right.
But what are these properties, and why can't you just find any sample in the vicinity, and why do you need to have the prototypes there in place?
Thanks. So the question, just to repeat the question is how do you find the prototypes? Why don't you pick random data points as prototypes?
Yes.
So the way, the algorithm that we used for coming up with these prototypes, they model it as an optimization problem, right? So you can obviously find more details in the paper. I can send you the paper. But to give you a gist, they model it as an optimization problem, wherein the objective is you want to find as few data points as prototypes as possible, right? You don't want, if there are 100 data points, you don't want 99 of them to show up as prototypes. The second is, the prototype should cover as many data points of the same class as possible, right? So if you go back to this example, so you want the blue prototypes to be lying in a region where there are a lot of blue prototypes and green prototypes covering a lot of green prototypes and so on, right? So you want a prototype of a class to cover as many other prototypes of the same class. So, right? So if you do that, then you get some reward. On the other side, you don't want the prototypes to cover data points of the opposite class, right? When you don't want the blue prototype to cover data points of red and green classes. That is the second. And the third is you want the data point to be covered by at least one prototype, right? So you don't want the data point to be left out. So it's modeled as an optimization problem based on these desirable properties, and you solve the optimization. You say that it's computationally infeasible to come up with the optimal solution. Then they use a greedy approach to come up with an approximate solution, and that is how we do it.
Thank you.
Welcome.
Hello, thank you for your presentation.
Thank you.
What procedures do you use for generating the random lines?
Sorry?
What procedures do
Okay.
you use for generating the random lines?
So just to repeat the question, what procedure do you use to generate the random lines? There is no procedure as such. It's truly random, right? So as I mentioned, the idea is if two data points are close by, then the probability that a random line will split those two data points is very small. So you use that notion, and yeah, there's no specific procedure as such.
Hi. I was wondering if you're using this in production, and if you did a comparison to Lime, how did it compare?
So as I mentioned, there are two ways of comparison. One is with the accuracy. So when we compared, we did it on a different bunch of data as compared to Lime, and we did notice that our methods were close to 99% accurate. So in terms of accuracy, we were good enough. And in terms of user study, again, I mean, the comparison there is not apples to apples because we are looking at a different bunch of data as compared to what Lime was doing. So also another point to note here is predominantly in literature, if you look at these interpretation-based models, they look at either they work with image data, wherein you are trying to explain cat versus dog, or they look at text data, wherein you have a sentence and you are trying to come up with sentiment analysis and say which words are positive and negative and so on. In our case, we wanted to apply it on tabular data, which is the kind of data that we work with. So essentially, it's say all the machine-generated data that you have in terms of people's product usages and web usage, and then trying to, the models that we have are trying to determine who will convert and buy Adobe Photoshop and who is likely to churn out of the subscription and so on. So that data itself was different, and hence there is no, say, apples to apples comparison.
And what's next for the development of this approach?
So as a next step, what we have done is we have created a framework. I skipped the slide thinking that it is not probably too relevant. But in our system, we have 3 components. We have a backend system, which works off of Spark Scala, deployed on Databricks. What we do is that system computes all the pairwise distances, comes up with prototypes, and as well as global explanations. And then we have a middleware component, which is a Python Flask application, which builds REST APIs where you can access either global interpretation for any of these models, or you can give in local single data point and retrieve local explanations. And then we are working on building a user interface to access these.
Thank you.